other minor components. So today we'll be discussing about the one more very important component, that is the propeller. Okay, so let me on the software. See, in this open VSP we have done with the pod, fuselage, wing, stack, blank, ellipsoid, body of revolution. So next component what we have, the propeller, prop in the sense the propeller component. Okay, so as soon as we add this component we can able to see the default component, default geometrical part of this propeller. Okay, so I'll discuss about this later. Let me first cover the theory part. So as we know, the propeller, okay, propeller, we can say that this is a device which transmits power by converting it into a thrust, okay, for propulsion of a vehicle, like our propeller kind of vehicles what we have, the turboprop aircraft, or the engine which will be using, that is the turboprop engine. Okay, so generally we can say about this propeller, like it is a device which transmits power by converting it into a thrust for propulsion of a vehicle through a fluid medium by rotating two or more twisting blades, like or more than two, like this what we have, one, two, three, four, five, six, and in this case one, two, three. So by rotating two or more twisting blades about a central shaft. Okay, here we have in a manner analogous to a rotating a screw through a solid. So these blades, what we have, okay, the blades of a propeller acts as a rotating wing, and these blades produces a force through applications of Newton's third law, and it will generate a difference in pressure between the forward and rearward rearward surface of this aerofoil blades. Okay, if we take the cross sections of this blade, we can able to see that cross section is like aerofoil shape. Okay, so that's why this propeller, it's a device which converts rotational energy and generates whatever the energy it will generate, that will be done by a engine or any other mechanical source, okay, into propulsive force. And we have different type of propellers, like a fixed propeller, okay, and wooden propeller, and metal related propeller, ground adjusted propeller, and applications of a propeller, like for different aircraft, P-51 Mustang, micro air vehicle, MAV, small propeller. So like this we have different aircraft with the different propeller configurations. So these are the terminologies: tip, trailing edge, face, propeller axis, bush cap, blade, boss, propeller shaft. Okay, so as I told that propeller, here we, yeah, in this case we have three blades. Okay, so these blades of a propeller acts as a rotating wing. Okay, and these blades produces a force through the applications of Newton's third law, and it will generate a pressure difference between the forward and rearward surface of the aerofoil shapes blades. Okay, see here, like different propeller with the terminologies: blade root, the stern, trailing edge, blade tip, pressure surface, leading edge, and suction surface. So this all terminology will be not denoting in our OpenVSP software. Already inbuilt things is there. Just we have to change these parameters. That's it. Okay. Just for understanding purpose, I have included this slide. Okay. Because in OpenVSP we will not be dealing with this all theory things and all. Okay. So here see the design concept, but we have the important definitions with respect to the propeller, the parameters. Okay, advanced ratio, rotational speed, propeller diameter, available power, shaft power, torque, thrust, available thrust, flow velocity, thrust coefficient, power coefficient, blade orientation with respect to zero lift line, overall efficiency, propeller efficiency, drive motor efficiency. So these are the parameters, okay, so which will be defining with respect to our propeller. So the design concept, what it states that okay, the number of blades be okay, has small effects on the efficiency, okay, and propeller with more blades performs better efficiency, okay, and axial flow velocity, it means flight velocity, okay. Large pitch propeller may have a good efficiency at design point, but may run into trouble at low axial velocity. Blades tends to stall, so that's why it's very important to even know the axial flow velocity of that propeller, okay, and the diameter, okay. Larger diameter tends to give higher efficiency because of increased mass flow rate, right? So usually the best overall propeller have a pitch to dia ratio of 1, like this. And here even we have the lift and drag distribution as I shown in this slide. Okay. So lift and drag distribution instead of CL and CD, okay, it is a convenient to specify a radial distribution of polar and design angle of attack. So the distribution of CL and CD can then be examined. Okay. So for good performance, L by D should be high. Also, it is better to use a low angle of attack for design. So tip section, root section, the cross sections from this end to this end. Okay. So that's also very important. The tip section of an propeller operating at greater than 0.7 Mach should be designed to operate at small CL, that is less than 0.5, like that. Okay. So and with respect to density, if I tell, okay, so no, this propeller efficiency affects even the size and shape of that complete parameters. Okay, design parameter. And here we have the CT and CP are not affected by the design, but thrust and power are affected. Okay. So for air propeller, the performance of a propeller and engine depends upon the altitude also. That is the density. So that's why what we can say that the propeller engines are preferred in a low altitude and short range purpose. Okay. And this propeller what we have all initially no all propeller started with all whatever engine before they used to use, okay. All aircraft propulsion started with propellers and piston engines, as we know. So that see here we have different old aircraft, okay. So by looking to this aircraft we can say that aircraft propulsion system, okay, or aircraft propulsion started with the propellers and piston engines. Directly not we have jumped to turboprop or turboshaft or gas turbine engines. No. So aircraft propulsion system started with the propeller and piston engines. Okay. So see here we have the other terminologies: trailing edge, hub, leading edge, cord, blade tip, leading edge. Okay. So and the clear blade view is shown in this slide, that is the blade tip, leading edge and trailing edge. If you take the cross sections of this blade, of course the shape will be like aerofoil shape, because we know why we are keeping the aerofoil shape, because of the pressure difference and will be generating a high thrust. Okay. So propeller efficiency is determined by propulsive force output by shaft power in. So that is the thrust into axial speed divided by resistance torque into rotational speed. That is T into V. That is thrust and axial velocity to the resistance torque rotational speed. So those parameter will give the propeller efficiency. Okay. The thrust developed and the power required for a propeller are given in terms of thrust efficiency, thrust coefficient and power coefficient. That is CT and CP. And the forces and stresses acting on blades, those are also very important to know, because the forces acting on propeller are like a thrust, centrifugal force, torsion or twisting force. Though these all uh, parameters, or these all kind of different forces which will be impinging on the propeller. Okay, like thrust, that is the air force, because of the air force, as we know. Okay, air force on the propeller, which is parallel to the direction of the advanced and induced bending stress in the propeller. And the centrifugal force. Okay. So here centrifugal force, if I talk about the centrifugal force, we can say that it is caused by rotation of a propeller and tends to throw the blades out from the center line. Okay. And torsional or twisting force, that is the blade itself, right? So that is caused by the resultant of air forces, which tends to twist and the blade towards at a lower blade angle. So here we have different propeller, like three with twisted angle. So like this twist we can give in our open VSP software. Okay, then we have different propellers. The shape and the design parameter is different, so that's why the overall look of this propeller is different. It's not the same. So this kind of different propellers we can create in our OpenVSP just by altering the design parameters. Okay, so it's not hard to design. Just if you alter the parameter, once you know the design parameters correctly, just input the design parameters. So based on the design parameters, you'll get your required propeller. And these are like our aerodynamic principles, uh, which we don't need our OpenVSP, but just for understanding purpose, I have included this slide, which we have studied in our UG level, right? So even you can increase your pitch, okay, based on the pitch angle. Okay, low pitch, high pitch, and full feathered 90-degree. So based on these parameters, you'll be getting the design changes in the OpenVSP software. Okay, as I told you about the low pressure and high pressure, these all like principles based on these propellers, the configurations of the propeller and the change in the propeller parameter. So we have different aircrafts, like a tractor type, pusher type. Okay, so if you are placing your propeller forward, then we can say it is a tractor type of propeller. If it is back side, then pusher type, rear side. Okay, now we will go to OpenVSP software. So here we are showing the different aircrafts. Why? Because just to give idea about the OpenVSP software. Okay, so once you plan to design this kind of aircraft, or just a dummy model, okay, just for analysis purpose, or to complete your conceptual step based on the design parameters. Okay, so that type of design even you can complete in the OpenVSP software, and you can model your required aircraft like this. So now we will jump to the open VSP software. Let me on once again. See, as soon as I double click on the software, we know we have to select the geometrical component, that is the propeller, and I will add the propeller. So as soon as I add here in this open VSP window, I got the default propeller with default parameters. Okay, in the general tab. Okay, in this the same thing what we have seen for our different components like a pod, fuselage, wing, stack, blade, ellipsoid, body of revolution. Okay, in this case, what was there in a general thing. Similarly, here we can able to see for our propeller component. Okay, so I will not tell anything about this because if you want to translate your component along X, along Y, along Z, similarly, if you want to rotate, just use this tabs. Okay, and next we have subcomponents. This also has been discussed so many times. Okay, so I will not jump to these three tabs. Directly I will go to the design parameter. Okay, see in this design parameter we have the propeller based parameters, that is the diameter, number of blades, okay, and other parameters like with respect to the tip treatment and also with respect to the overall propeller from root to tip, from leading edge to trailing edge. Okay, so just observe the changes. Okay, in this design tab, here we have the diameter. So currently the default diameter is 30 unit. I'll change this 30 to 10 and I will enter. The overall propeller dia has been changed from 30 to 10. Let me change the view. Yeah. So like this you can increase your propeller diameter. Okay. So instead of three propeller, if you want more than three, okay, instead of three, if you want four or five or six, just type that number here and enter. Okay. Now see the currently the reference of this propeller is at 0 comma 0. If you want to rotate this reference propeller, then you can rotate with respect to the angle, that is 10 degree. If you give plus 10 degree, okay, then you can able to see this reference propeller has been rotated, okay, in a anti-clockwise direction because of the positive 10 degree. Okay, now instead of positive 10 degree, if I give negative 10 degree, then it will rotate in a clockwise direction like this. So this red mark, it indicates that this propeller is a reference propeller, and whatever we are rotating, okay, or else whatever the angle I am giving here, okay, so that angle is changed from 0 to 10 degree. Okay, so minus 10 indicates this reference propeller is rotated in a clockwise direction. Okay, Now instead of minus 10, if I give minus 50, then just observe the changes. So see, from here, the reference propeller has changed its angle, that is 50 degree in a clockwise direction. Similarly, instead of minus 50, if I type just plus 50, then this reference propeller will come here. Okay, I hope you have observed the changes, right? So like this, if you want to rotate your reference propeller, you can rotate, and you can adjust your reference propeller as per your required place, okay, or the location. And next parameter we have the beta 3 by 4. Currently it is 20 degree. Beta 3 by 4 in the sense the twist angle, okay. See this all blades has been twisted 56.08 degree. If you don't want to twist, then just type 0 and enter. Now again I will change 0 to just 20 degree. See here, it has been twisted a little bit, right? It is 20 degree. Now still if you want to twist, then just enter 60 degree. Right? Again, like plus 40 degree has been added to that 20 degree. So that's why the overall twist is 60 degree. I'll shade, just observe the changes, okay, for 60 degree and for 0 degree. Okay, so I'll just change 60 to 0. See, the view is completely different, right? Let me keep this in ISO view. Geometry is not that much smooth, so that's why what I'll do, I'll just increase the number of tessellations. Okay, see, I'm increasing the number of tessellation instances. I'm increasing the wireframes, okay, because to smooth this propeller geometry. So for smoothing your geometry, you have to increase the number of tessellations along U and W. Okay, now you can shade. Yeah. Next we have construction by C. Let me convert this into shaded. Yeah, no need to shade. Just I'll change the shade into wireframe, and I'll just decrease the number of tessellations. Okay. See, constructional X by C. Construction X by C in the sense. Wait, let me. Yeah. So here, this propeller geometry what we have, the component. Okay, I'll share this. Okay, this construction X by C one indicates that one face, that is the leading gauge, is completely flat. Okay, and the opposite of that part, that is the trailing edge, is not a flat, or it's not a straight. So to maintain the symmetry, what we have to do, instead of 1, just type 0.5, and you can able to see symmetry. If we cut this propeller, then we'll get equal parts once we construct the X by C 0.5. Okay, so instead of this, if you just type 0 and if you enter, then the trailing gauge, that will become completely flat. Now if I change this 0 to 1, then we will get the opposite of this. Okay, opposite of this in the sense, leading edge will become flat. Okay, like this. See the cross sections, it's a aerofoil shape. Let me share this. Yeah, okay. So I'll just maintain this construct X by C 0.5, and simultaneously you can change the feather axis. Wait a minute. Yeah, okay. Now I'll change the feather axis. Feather axis you can change. I mean, like this reference axis what we have for this feather. Okay. This you can alter. So with respect to that, for feather axis, even you can give the offset for that feather axis. So whatever feather axis and feather offset changes you do, that will affect to your reference propeller. Okay, and similarly it will affect to the other propeller what we have. Okay, and here next we have the tip treatment. Okay, let me take the wireframe mode. Yeah, so you can change your tip treatment. Okay, the flattened into round root cap type you can change. See, it has been changed. Okay, for this propeller, reference propeller. As I told you, whatever changes if you do to reference propeller, okay, that will affect to the other propeller what we have. Okay, so instead of rounded root cap, even you can choose the edged or sharp or flat. Okay, as per your requirement, whichever root cap you want, just select that root cap, and that root cap will be added to your propeller's tip side. Okay, so root is done. Now similarly you can do changes to your tip cap. So yeah, here is our tip part. So currently it is rounded. You can change rounded to flat. Just observe the changes. Initially it was rounded. Like this you can change the tip cap type, rounded into flat, edge or sharp. Okay, and with respect to this, even you can change the tesselation control near the leading edge. Okay, and trailing edge. Let me decrease the number of wireframes so that you can observe clearly the leading edge and trailing edge clusters. Yeah, so purposely I will decrease the number of tessellations just to show this parameter, that is clustering. I mean, like, you can increase the number of tessellations, or you can control your tessellations leading edge side and trailing edge side. Or else you can type the number. So like this you can control your tessellations. Okay, leading edge side and trailing edge side. Or else you can maintain a normal tessellation. Similarly, you can control the root clustering and tip clustering. So here I am disturbing to tip clustering. That's why you can able to see tip side change in the cluster. Just type 3 and enter. Instead of 3, just type 5. Let's see. Changes here. See. So tick cluster is increased. Okay. Similarly, root cluster you can increase. If you don't want to increase, just type lower numbers. 2.2 or 3. And after this, you can just increase the leading edge clustering, trailing edge clustering, or just even you can increase overall tessellations. Okay, so these all changes we will do only when we need a smooth geometry and all. Okay, and design. Okay, so today design is done. Okay, let it be. So still many things are there to discuss about the propeller. That is blade, sections, modifications, and all. So these three, whatever we have, these things I'll complete tomorrow. I mean, like tomorrow's class. That is the propeller class 2, or creating a propeller class 2. Today I have discussed about the introduction part and the design parameters of propeller component. So whatever we have the other parameters, the blade, cross sections, modifications, fold and all. So these things if I discuss now, it will take time. No problem. For today, this much is enough. Tomorrow I'll be going in a deep about these tabs, because propeller geometry is very important. I mean, in one class, this is not good. Okay, to discuss all component or all parameters. So we'll keep this four tabs, one, two, three, four, for our tomorrow's class. Okay. So thank you to all. We'll be continuing tomorrow. Thank you.
Okay, thank you, sir.